All right. So M in P. The partial derivative of P is 0 with respect to anything, but with respect to Y. The partial derivative of N with respect to Z. You see any Z terms? I don't, so it's 0. Partial derivative of P with respect to X is 0. Partial derivative of M with respect to Z. Do you see any Z terms? Nope. 0. Partial derivative of N with respect to X. So it's just negative e to the X sine Y. So negative e to the X sine Y. What about the partial derivative of M with respect to Y? What's the derivative of cosine Y? Negative sine Y. Oh, well, guess what? That's the same term. All right, so we know that it is conservative. So now that we know it's conservative, we can figure out the potential function of f. So how do I figure out the potential function? I'm going to have to integrate m with respect to x because of the I. So I want to integrate this with respect to x. There's only one x term. What's the integral of e to the x? E to the x. Now, your n has this negative in front. Don't forget that. So I got to integrate n. So it's negative e to the x sine y with respect to y because of the j. So the only y term I have is sine. The integral of sine is negative cosine. But there's a negative in front. Negative of negative cosine would be positive cosine. So it's e to the x positive cosine y. Okay. And then the integral of 2, because of the k, it's with respect to what? Z. What's the integral of 2? 2z. All right, so we have, if you, and of course, like Harmony pointed out, she said, well, what were those extra things? I mean, right here you would have plus some function of y and z. Here you'd have some function of x and z. Here you'd have some function of x and y. But it's not really going to matter for what we do. We take all the terms once and then put plus k. All right, so our potential function, that's what little f stands for, the potential function, f of x, y, z is going to be equal to, take each term once, so e to the x cosine y plus 2z plus k. All right. So work is equal to the line integral over c of f dot dr, which we're not going to calculate because we don't even have the r, right? We're just going to say that's equal to the potential function evaluated at, I didn't give you the points, so let me give you the points. I gave you the force field. Here's the 2 points. From 0, pi over 2, 1, to 1, pi 3. So the path does not matter because this is a conservative force field or vector field. So it must have path independence. So it must be simply connected. All right, so it's going to be f of, you evaluate the first point, 1 pi 3, minus f of 0 pi over 2, 1. And remember, this is x, this is y, this is z. This is x, this is y, this is z. Alright, so let's work that out. We have our, what is that again? What's that little f called? Potential function. Alright, so we have, plug in a 1 for the x, it's going to be e to the first times cosine of y, so cosine of pi plus 2 times z, so that's 2 times 3, minus, now plug in a 0 for the x, that's okay, e to the 0 is just 1, times cosine y, cosine of pi over 2, plus 2 times z, z is 1. Alright, so that's going to be e times, what's the cosine of pi? -1 plus 6 minus e to the 0 is 1, but the cosine of pi over 2 is 0 plus 2. So I have negative e plus 6 minus 2, or negative e plus 4, or how about 4 minus e, because that looks better. All right, what would happen if my object, or whatever I have, traveled from this first point to the second point, and then from the second point back to the first point? What would the work register as? It wouldn't be double the work. That's not how it would work out if we worked out the integral and we plugged in the points, we would get 0. Because remember, work can be negative. So you have to keep that in mind if you travel from one to the other, and then from the one you ended at back to the first one. If you work it out using the fundamental theorem of line integrals, you're going to get a 0, because you can register work as being negative. How have y'all dealt with that in physics? I mean, do you ever get a negative work? Did y'all ever get any negative work going? Well, you probably didn't go through any fields. So y'all should have done some stuff with magnetic fields. Oh, okay. Probably because y'all weren't in Cal 4 and y'all couldn't, like, because y'all did that in physics too, right? Yeah. It's hard to be able to do this kind of stuff if you can't integrate partially and solve differential equations. You could do all this before we even went over it. All you got to do is know about partial derivatives and partial integrals. All right, one of the main things, I guess, that that this is trying to tell us is that we really have two different ways to work this out. Okay? If we know that f is conservative, big F, the vector field, then we can work it out with a line integral, and we'll have path independence. And also, if you have a closed curve, like this up here, well, this is a bad closed curve, but, you know, if it was going, if you go from this point to this point, this is not a closed curve, but this would be a closed curve. So the work done for any closed curve is going to be 0 for a field, because it's going to, you're going to get a positive value, and then you're going to get that negative value. So even if it went from here to here, and then 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 it went from here to here, it's still going to be 0 if it's a closed curve, if you add up all those. But you have options, is what this is trying to tell you. So if you know the path that something takes, you know, it looks like, let's go back. It looks like that. That might not be the most efficient way to work that problem. Especially if I don't give you the path, or you can't easily figure out the path. What would be the most efficient way if it's path independent? Why not just draw a straight line? It's a lot easier to come up with a path, your R of t, if it's a straight line, than it is if it's all this crazy stuff going on. And if it's going to do, if you're trying to figure out work, why not do it the easier way? Why not come up with a path of a straight line going through 2 points, which we've been doing. If you think back to algebra, you can find the equation of a line that travels through 2 points by figuring out slope and figuring out, you know, all that kind of stuff, x-intercepts, y-intercepts. In 3 dimensions, you'd have to add a little bit, but in 2 dimensions especially, you could figure out the slope of a line going through 2 points and then figure out the equation of the line very easily. So I guess that's kind of the main point of all of this, is that yes, we can work it out using the integral, line integral of f dot dr, but if it's conservative, we know it's path independent. If it's path independent, then we can make any path that we want, as long as it goes, starts at that initial point and ends at that terminal point. And sometimes a straight line is easier to work with than some crazy curved line like that you would probably have to partition into different parts, or break it into different parts, and then have more than one integral to work with to be able to find it, or more than one path to work with, and then from that, you know, it's easier. If it's easier to make a straight line, make a straight line, is basically what it says. What your book says about that, technically, it says, you have options for evaluating a line integral involving a conservative vector field. You can use a potential function, or it might be convenient to choose a particularly simple path, such as a straight line. Okay. So here's one like that. I'm not going to make you work through another one right now, but I want to show you one. Let's just look through it real quick. All right, evaluating a line integral. So evaluate this line integral for this force field, and it says C sub 1 is the semicircular path from 0, 0 to 2, 0. So you see that? The semicircular path. Well, to write a semicircular path, this is the way it has to be written, because you're going in a circular motion. All right, so it's 1 minus cosine Ti plus sine Tj. However, there's another way to do this problem. Why not do the same integral with that straight line there? Look at its path. It's a straight line. It's Ti. Right? Plug in a 0, get out a 0. And then plug in a 2, get out a 2. So I don't know about you, but if I have to do integrals, f dot dr, I got to do an integral or whatever, or even if I don't, if I have to find a potential function, it's easier to use a straight line. So it says you can go through, you can find your dr, then you can dot it with the vector field, and it said in your t they bound between 0 and pi. And look what you have to integrate. All right. It said this integral should dampen your enthusiasm. Does that dampen your enthusiasm? Maybe I'll put that one on the test if it doesn't. Well, how about, so B is, why not just find the potential function? Why worry about the path? Find the potential function. Plug in the second point, plug in the first point. There you are. That's probably the easiest way. Okay? But if you did want to work it out, since you know that it is conservative, you could find dr, well, it was ti, r was ti, so it would be I. Then if you plug 1 back into your vector field, this is what you get. So when you take the dot product, this is what you integrate. They must have defined a path from 0 to 2, which makes sense because of where it went to. It was from 0, 0 to 2, 0. So it makes sense to make it 0 to 2. And then you'd get 2. It says, of these 3 options, the third is obviously the easiest. It probably is, actually, because you don't have to find the potential function, right? You still, to work it the second way, you still have to take this and do some integrals and find the potential function. And then plug in the points. But the third way, if you know that this path is just t times I, because there's no change in the y at all, then the third way would definitely be the easiest. Okay. All right, not going to do that much on the next part of the section, so we're just going to run through it really quick. Even though some of you may be interested in it. It's not because I'm about to run out of time, it's just because we're not going to do a lot with it right now. And it's conservation of energy. All right, so in a conservative force field, the sum of the potential and kinetic energies of an object remains constant from point to point. So there's the equation for kinetic energy. And for potential energy, we find of P, let's see, going at a point, define P as the negative of the potential function. All right, and yeah, so basically can do kind of the same thing, but it's a little, it's just a little different. So the work done along F is P of A minus P of B. Okay? Yeah. Thanks, Faraday. All right, but I just wanted to show y'all that. So it is applicable to, y'all probably did that in Physics 1. All right.